Hi, so let's continue our AVL balance tree implementation. So far we have implemented the set balance and the height methods, which are the fundamental basics of rebalancing a tree. So as you may recall, there are four situations. One, we have to make one single left rotation or a single right rotation, or there may be cases where we have to make a left and a right rotation, or a right and a left rotation, according to the situation. So we have to check whether the parent node that balance is less than -1. As you may recall, we have to make rotations if the balance number is less than -1 or if it's greater than +1. It means that our tree is definitely unbalanced. So we have to check whether the self.height of the parent node dot left child is greater or equal to the self dot height with the parent node dot left child, right child. And if it's true, then the parent node is equal to self.rotate right. We have to make a single right rotation with the parent node, and we haven't implemented this method so far. And else we have to make parent node is equal to self. We have to make left and right rotation. So rotate left, then right on the parent node, of course. Rotate left and right. I think I have to check whether the parent balance is greater than +1. I think it's not less than equal. It is this. It has to be less than. Okay. If it's greater than 1, parent node that balance. Okay. If the balance node that balance is greater than 1, I have to check whether the self.height of the parent node that right child dot right child is greater than or equal to the self.height of the parent node that right child that left child. And if it is so, then we have to make a left rotation. So the parent node is equal to the self.rotate left on the parent node, of course. And else we have to make the parent node is equal to we have to make a right and a left rotation. So self.rotate right, left on the parent node. These are the methods. So we have 4 situations. Okay. And if we have to check whether the parent node of the parent node is not none, then we have to rebalance the tree on the parent node that parent node, else we just self root node is equal to the parent node. Okay, so that's all about rebalancing the tree, and of course we have to implement the methods. So for example, we will have a rotate left right. It's going to have a self and a node, and I'm going to print out that rotation left right. Okay, and note that left child is equal to the self that rotate. We have to rotate right. So yeah, now we have to rotate left. We have to rotate left first, and on the left child, and then we have to return the self that rotate right. So we rotate left and then rotate right, and I think the rotate right is going to get a node, okay, as a parameter. So I think wrong indentation. Okay, def rotate right left. It's going to have a self and a node. I'm going to copy and paste it. Just switch them right, right left, and rotate right left. Now we just have to know that right child is equal to the self that rotate right. I just have to rotate right on the node that right child, and have to return the self that rotate left on the node. Okay, what's the problem? Bad indentation. Okay, okay, so we just have to implement the rotate left, def rotate left node left, and the def rotate right. Okay, so as far as rotation left is concerned, we have to, first of all, I print that rotate left. Okay, first of all, we have to make a temporary variable, the node that right child, and we have to set the parent node of the B to the node that parent node. Okay, then we had to set the node that right child is equal to the B that left child, and we have to check whether the node that right child is not none. If it's not none, then the node that right child that parent node is equal to the node itself, and we just have to set the left. I think it's just the basic algorithm. You can search it on the internet. it is specified how you can make rotations with the help of AVL trees. The professors of MIT and Princeton made these as efficient as it can be. So I think the best way is to follow them in their direction. Okay. So the left children is equal to node, and the node that parent node is equal to the B. Then we have to check whether the B that parent node is not none, and if it's not none, then we have to check whether the B that somewhere wow, parent node. Okay, B that parent node that right child is equal to the B. I mean, now we just have to specify, okay, B that parent node that right child is equal to the node, the node itself. Then we have to be that parent node that right child is equal to the B, and else we have to be that parent node that left child is equal to the B. Okay, of course, after this operation we have to set the balance for the node and for the set balance to the B as well, and return the B. And why? Because there may be the case that after the rotation there's become a situation where it is unbalanced too, so it gets into an unbalanced situation, so we have to check again and make the rotations if necessary. So that's the left rotation, and the rotation right is quite the same. We just have to swap some rotation. Yeah, we just have to swap some rotations. Rotate right, print rotation right. Okay. So first of all, we have a B equals to node dot left child. We set the parent node of B is equal to the node that parent node. Okay, we set the node dot left child is equal to B that right child. We have to check whether the if node dot left child is not none. Then we have set the node that left child, that parent node, is equal to the node itself. We have to set the right child. Right child of the B is equal to the node. We have to set the node that parent node is equal to the B. We have to check whether the B that parent node is not none. And if the B that parent node is not none, we have to check whether the B that parent node that right child is equal to the node. And if it's true, then the B that parent is that right child, of course, is equals to the B. Else the B that parent dot left child is equal to B. Okay, and we have to solve self.setBalance on the node and self.setBalance on the B, of course, and have to return B. Okay, so let's test it. I think there will be bugs, but let's give it a try. I'm going to from AVL dot balance tree import balance tree. So I'm going to have a tree. It's going to be a balance tree, of course, and I'm going to insert the example we have discussed so far. So I'm going to insert the tricky numbers, for example 4 and 3 dot insert 6, and if I insert a 5, we should get a right rotation and then a left rotation. So let me run as Python run. Yeah, and we have a right rotation, so we have a right-left rotation. So first we have a right rotation and then a rotate left. And that's why it is printed out, because the right rotation calls the right and the left rotation, and the right rotation prints it out, then the left rotation prints it out. So it's working fine. If the situation is the same that on the other hand, so if it is a left-heavy tree, such as like it's 2 and 3, if you think that the 4 left child will be the 2 and the right child of 2 will be the 3, and it's when we are unbalanced, we have to rotate left and then right. So let's check. And yeah, we'll rotate left and then right. And let's check whether the, for example, in order operation, traverse, how do we call it? Balance tree. Maybe nothing. Okay, so def traverse in order, and we just have to call the root node. Maybe we should check whether it's null or not. We are not going to do it. Traverse in order. I think it should give us the numerical ordering. Yeah, 2, 3, 4. Very, very good. So maybe it's not so easy to get a good grasp of rotating trees, but it definitely worth the effort, because if the tree gets unbalanced, and it may get unbalanced if we have several items you want to insert, then the searching and deletion operations will reduce to linear time complexity, and for a database, for example, it is not so efficient. So we can do better, we can do logarithmic time complexity, we just have to make these rotations. So thanks for watching.